All right, folks. Sort of taking a break a little bit from grading. I'm going to get back to it afterwards, but I wanted to start making some of these Zoom recordings for Chapter 4, since a lot of you are already starting to work in Chapter 4 or should be working in Chapter 4. And 4.1, the first section in Chapter 4, is really using what we refer to as the first derivative test. Except for these functions, you're going to be looking at them on a closed interval and not the global interval. Now, what I mean by global, I mean from negative infinity to positive infinity. And we're going to be looking for maxes and mins, which means that if this is on a closed interval, keep in mind that we're going to have to test each of the endpoints of the interval to decide which of these are absolute maxes, absolute mins on the interval, and what the book refers to as local maxes and local mins. Some books call them relative maxes and relative mins, but this one uses the language of local. So here's the first function we're going to look at. Okay. Nice, friendly trig function. X plus 2 sine x. Okay. And yes, we're going to need the first derivative for all of these because, as I said just a minute ago, this is an application of the first derivative test. And so first, let's take the derivative of y prime. First derivative, that is. So we have y prime is equal to 1 plus 2 times the cosine of x. And as part of what the first derivative test is asking us to do is to find where we have horizontal tangents to the curve. Those are going to be critical values. They might be maxes and mins. We don't know. I'm telling you this ahead of time. Now, for most of these problems, they will be either relative or absolute maxes or mins, or again, what the book calls local maxes or mins, or absolute maxes or mins. So we set the first derivative equal to 0 because horizontal lines have a slope of 0. So we'll set this first derivative equal to 0 and then solve for x. Now I chose a trig function here because in order to solve trig functions, now if this were just a regular polynomial function or a rational function, it really wouldn't be that hard to solve this. But I chose a trig function because for most of you, it's going to require that you have a unit circle handy. Okay, and keep in mind that there could be more than one solution on the interval. In this case, I chose the interval to be 0 to 2 pi. All right, so I'm going to set this. I'm going to bring the 1 over to the other side. So I have 2 cosine x equals -1. And then I have cosine x is equal to -1/2. Now I could go ahead and just take the cosine inverse here of -1/2, but basically notice what this is asking is where is the cosine on that closed interval equal to -1/2? Well, if we know our unit circle, we know that the cosine is negative in the second and third quadrant. So if you take a look at your unit circle, I mean, because you're not going to really be able to use your calculator here. Calculator will only give you one solution anyway. But the cosine of x is equal to -1/2 at x equals 2 pi over 3. and at x equals 4 pi over 3. All right. Now, again, you should have your unit circle in front of you, and you should certainly be able to verify that if you don't already know this. Okay. Now we have 4 values to test on that interval from 0 to 2 pi. We have the 2 values of x that we just found at 2 pi over 3 and 4 pi over 3. And then we have the endpoints of that closed interval, one at 0 and one at 2 pi. And what I'm going to do here for your viewing pleasure is I'm going to plug the function into my calculator, just so I can see what I'm looking at. It'd be nice to be able to visualize. And if I set my window correctly with a little bit of playing around, we can see that. Okay. Now remember, we're not looking at this whole thing from negative infinity to positive infinity. We're looking at it on this closed interval. So what I'm going to plug in is first the 2 pi over 3 and the 2 pi over 3. So I'm going to go second, calculate value 2 pi over 3. Oops, hang on 1 second. Second, calculate value 2 pi over 3. And we can see it's exactly where we expect it to be. Okay. Right at the top of one of those humps. Right at the top of the first hump, that is. Now, the approximate value the calculator has given me, and I'm just going to use decimals here, guys. Don't have to use exact values. I'm going to use y is equal to 3.826. And keep in mind that that's an approximate value. And I'm also going to check out 4 pi over 3. So again, in my calculator, I do the same thing. By the way, you should be checking this out too. Second, calculate value 4 pi over 3. And again, it's exactly where it's supposed to be, right at the bottom of that valley there. So one at the top of the hump, one at the bottom of a valley. And we already know, or should know ahead of time, one of these is going to be a max and one of these is going to be a min. Question is, what kind of max and what kind of min are we dealing with here? We haven't gotten that far yet. But I'm going to write down this value as 2.457 approximately. Now, the other points I'm going to test is the endpoints at x equals 0 and x equals 2 pi. Now, at x equals 0, it's going to be 0. Y equals 0. I could use my calculator to show you. And at the other one, it's going to be second, calculate value at 2 pi. And my calculator says it's about 6.283, which, by the way, is 2 pi. 6.28. All right, so let me show you all these values now. Now, what I'm going to do is I'm going to use the y values to declare which of these is a relative or local min and max or an absolute min and max. Now, the y equals 0 is certainly the smallest value that I've collected here. So that's an absolute min. So over here, I'm going to write here that this is an absolute min. And over here at the 6.28, that's clearly the greatest value of y. and that's an absolute max. Okay. That means that the other two, the hump and the valley, are going to be what we call local. So this is I'm using this language because that's what the book uses. This is a local max at the top of the hump. And this is a local min at the bottom of the valley. Okay, so I've tested the endpoints and I've tested the hump and the valley. The hump is a local max and the valley is a local min. And one of the endpoints at 0, 0 is an absolute min. And the other endpoint at 6.28 is an absolute max. And this is an application of the first derivative test. Even though they don't call it that yet, that's what we're basically doing. Okay. Now there's a whole bunch of homeworks in the book of all different kinds of functions. Not all of them are polynomials. I mean, not all of them are trig functions, but I chose a trig function because, and from my experience, it's going to be the one that's going to provide the biggest challenge to students in order to be able to solve this and come up with solutions. Got to have your unit circle handy. Okay. So over the next couple of days, I'll be making enough of these, so I should be well past the halfway point in this chapter with the Zoom videos. Okay. I'm going to end this. Goodbye.